Take a seat, Ron. Introduce you. Well, good afternoon. I'm Randy Hewlett, and welcome to the colloquium that kicks off our next few months of search talks, people that are applying for academic positions in our department. We have two positions, and the speaker today is Ruwan Senaratne. Ruwan is a graduate of Harvard University, the Rice University of the North, and he's went to graduate school after Harvard. He went to graduate school at UC Santa Barbara, where he did ultra-cold atoms. In particular, did an experiment on quantum simulation of ultra-fast dynamics using ultra-cold atoms. So he also, during his graduate career at Santa Barbara, made two entirely new apparatus, one for cooling strontium and one for cooling and trapping lithium. He then came to my lab to lead the 1D fermion experiments as a postdoc in my lab, and he has succeeded wildly in this endeavor. And we've had some really great results in collaboration with Han Pu and others. Ruwan is now a research scientist at Rice in our department, and he's applying for the faculty job that we have here, as I mentioned earlier. And Ruwan's kicking it off. So, Ruwan?
Thank you, Randy. Is this working? Can you all hear me? Okay, thank you, Randy, for the introduction, and thank you all for being here. It's good to be on the stage for once after being in the audience quite a few times. So today I'll be talking about those experiments in 1D that Randy mentioned. These are all experiments that we did or continue to do downstairs in the basement. So if you're ever down there, you can come visit us. We're usually there. So these experiments are studying a class of materials or a quantum system called Tomonaga-Luttinger liquids. And these are systems of quantum objects in one dimension. In particular, historically, electrons. But what we're doing here is using cold atoms, in our case, lithium-6 atoms, they're fermions, and we're trapping them in quasi-one-dimensional tubes. And what I have here is an artistic rendering of what one of these Tomonaga-Luttinger liquids might look like in a tube. We looked at the low-lying excitations in these tubes. And I'll tell you a little bit more about those. So first, I'll give a brief description about ultra-cold atoms before going into more about the theory and the experiments that we did. So first, atoms are very much quantum objects, and I sort of think of them as the quantum Rosetta Stone because they allowed early 20th century physicists to come up with quantum mechanics. Much like the Rosetta Stone allowed archaeologists to develop a translation between ancient Greek and ancient Egyptian hieroglyphics, atoms really allowed us to begin to understand quantum physics. And a lot of quantum mechanics was developed in order to explain atomic phenomena. Atoms are relatively simple, yet deceptively simple because the physics is quite so complex that it required creating a whole new branch of physics. And they're reproducible. If you have an isotope of an atom and you have one of those in one location, another in another location, they're the exact same. So you can perform experiments on them with confidence that what you're observing, it really has to do with the atom. And nowadays, there are incredibly precise measurements on atoms. So for example, some of the most accurate and precise clocks, these atomic clocks based on individual atoms trapped using optical trapping techniques. And you can get stabilities that are, a clock that might lose a second in the age of the universe. It's quite incredible. What I want to talk about is a little bit different, and it's about groups of atoms. And it turns out that groups of atoms are also quantum objects. And you can also think of them perhaps being simple in some ways and reproducible and tunable. There are a number of different ways to trap these cold atoms. One, which we use in the lab downstairs, is optical lattices. So these are interference patterns created using laser beams. They're standing waves, and often they're used to mimic the crystalline potentials that you find in condensed matter systems. Other platforms include optical tweezers, which are microtraps, individual microtraps that might contain individual atoms, as well as cavity QED, where you couple atoms to some optical cavity and you have photon-mediated interactions between the atoms or atom-mediated interactions between the photons. And there's, as Phil Anderson said, more is different, and there's a lot of different phenomena you can study. There's quantum phases, quantum phase transitions, there are topological states, you can study non-equilibrium dynamics in these systems, and much, much more. One particularly fruitful avenue is ultra-cold quantum simulation. And so the idea here is that you want to use atoms to simulate the physics of some other complex system. So this relies upon being able to create a mapping between your target Hamiltonian and the Hamiltonian that the atoms experience. And as I mentioned, optical lattices are really good for mimicking the crystalline potentials in condensed matter systems. A great example of quantum simulation is the observation of antiferromagnetic ordering that Randy did a number of years ago on the experiment that I work on, actually. So here they had a 3D optical lattice with fermions of two different spin states. And if you cool down to low enough temperatures, you get antiferromagnetic ordering. And this was observed using Bragg scattering. So this is an excellent example of the power of quantum simulation. And they're getting down to temperatures at which it's difficult to compute certain properties about these quantum systems at such large sizes. So a few more examples of quantum simulation from my own work. While I was a PhD student, as Randy mentioned, we built some cold atom machines with lithium and strontium. And in one experiment, we observed position space block oscillations for the first time. So this is with lithium atoms trapped in a 1D lattice. If you have a tilt on a periodic potential, quantum objects oscillate. And we actually saw this in position space, and this for the first time. We're also able to create hybrid Floquet block bands. So Floquet refers to when you drive the system periodically. And it turns out that you can couple block bands. So what I have pictured here are your first two bands in a block waves. And you can hybridize these bands by applying periodic driving. And this hybridized band, and we were able to observe that and map that new Floquet block band. We also studied quasi-periodic lattices. This was an experiment with strontium in a 1D lattice, in which we had some quasi-periodic order, incommensurate order. And it turns out that there's a whole class of excitations called phasonic excitations that don't exist in ordinary matter, but do exist in quasicrystals. But in real-life solid quasicrystals, these excitations are frozen out, and you generally don't have access to them. But within a cold atom system, you do. And so over here, what we show is that we were able to drive more than 10 different harmonics of the typical phonon interband transition using this phasonic drive. And lastly, what Randy alluded to is this project on simulating the ionization of an atom, which is experiencing an ultra-fast laser pulse. So here we use atoms to simulate an atom. So we had a BEC trapped in a tight trap, which we then wiggled back and forth. And it turns out that you can create a mapping between that Hamiltonian and the Hamiltonian that an electron experiences in an atom that's experiencing an ultra-fast laser pulse. And so this was kind of a prototypical experiment that sort of showcases the flexibility of ultra-cold atoms. And then I just wanted to spend a slide talking about maybe the next steps beyond these types of quantum simulation experiments. Neutral atoms in optical tweezers have recently become an emerging platform for quantum computing. So you can use individual atoms as qubits, and they have excellent coherence times. But the challenge is to implement multi-qubit gates or 2-qubit gates. And one strategy to doing that is implementing collisional gates. So what I have here is a depiction of a collisional gate that was done in an optical lattice a number of years ago. And what you do is that you have two atoms, which can be in in this hyperfine basis, 2 states, which forms your qubit. And you can allow them to interact, and that creates a quantum logic gate. And it turns out that you can do an operation which swaps the quantum state of those 2 initial states, and that's called a swap gate. And if you do that for half the amount of time, you get what's called a square root swap gate. So if you do one of these square root swap gates, you do it twice, you end up with the same qubit that you started with. And it turns out that that's a universal quantum gate that can be used in addition with single qubit gates to implement any kind of quantum gate that you want to do. And the advantage of this type of strategy to implementing multi-qubit gates is that it's very amenable to preparing fermionic atoms in entangled states, which you could then couple with quantum simulations to create or to probe perhaps previously inaccessible Hamiltonians, or to extract information from them in some novel way. So the rest of this talk, I'll be talking about work that we did here at Rice. So referring to those 1D experiments. The reason why we study 1D is that we can make very nice quasi-1D traps in our lab. So using a 2D optical lattice, you can make an array of quasi-1D tubes, and you can fill those tubes with atoms, and they behave in a one-dimensional way. And it turns out that physics in 1D is very different. As you can imagine, that the physics governing these classical balls in this ball pit is quite different from what you see here in this Newton's cradle. So even at the classical level, you can sort of see that physics in 1D is a bit different. And also, I'd argue that physics in 1D is important. As we go to smaller and smaller wires in solid state systems that people are pushing forward in the semiconductor industry, it's possible that we will get to the stage where 1D physics is important and possibly useful. So it's important for us to study these things. So now I will go on to talking about the Tomonaga-Luttinger liquid theory, which is the physics that governs electrons, for example, in one dimension. So first, a refresher on Fermi liquid theory. This is the theory that is generally used in 3D and 2D. And so here you have some Fermi surface, and below which, at sufficiently low temperature, you have a filled Fermi sphere in which you have a bunch of states, and there's a Pauli exclusion principle, so they all can't lie on top of each other, so you have some pressure which defines a Fermi energy. And any kind of, all the excitations that are allowed are just excitations around the Fermi surface. So for example, you can promote an electron from just below the Fermi surface to being just above the Fermi surface. And these are quasi-particle excitations. They're fermionic. You can generally think of them as being very similar to a free electron, except that they have an effective mass. So this is what the Fermi surface looks like in 2D. It's a ring. And as I said, any kind of excitation that takes you from the Fermi surface to the Fermi surface is allowed. And so you can imagine that you can have any type of excitation for which the momentum is less than twice the Fermi momentum. And so this is what I've plotted here is the excitation spectrum, and you can see that you have low energy excitations for any momentum. And this is sort of just a depiction of what a quasi-particle traveling through that system might look like. It looks very similar to a free electron, but it's slightly dressed. In 1D, this depiction completely fails because the Fermi surface, which was a continuous line in 2D, is now just two Fermi points. And so if you want to have an excitation, all you can do is stick around the original Fermi point where you're at, or you can move to the other Fermi point. So there's two possible momenta that you can be excited at, and that's what's depicted here. So in between these two momentum, there are no low-lying excitations. And if you look at close to zero momentum excitations, the dispersion is roughly linear. And it turns out that these excitations are collective excitations, similar to sound waves. This model was studied by Tomonaga and Luttinger in the 50s and 60s, but also this problem was studied by Bloch in the 1930s, almost 100 years ago. So the solution to the failure of Fermi liquid theory in 1D is Haldane's Tomonaga-Luttinger liquid theory. So in a series of papers in the early 1980s, Duncan Haldane proposed a new formalism, which he called the Luttinger liquid theory, by analogy with the Fermi liquid theory, in which you can create a description of of an interacting Fermi gas in one dimension. So this is generally accepted now as the formalism, but it requires experimental testing, and I will get to that later in the talk. So what does this Tomonaga-Luttinger model look like? So you move away from having individual fermions, or fermionic operators, free particles, to now considering density fluctuation. So instead of fermionic operators, you're now looking at density operators. And these density operators, you can allow them to either propagate left or right. And it turns out that they have bosonic commutation relations. And so this is the general description of a spinless gas of fermions in one dimension, is a bunch of density waves. The low-lying excitations are density waves. Once you add spin, an interesting thing happens in that the Hamiltonian sectorizes. So there's two sectors, one which is related to the density, and one that's related to the spin density. And so this is the density of both the up and down spins, and the sigma is given by the difference in the densities of the up and down spins. So you have low-lying excitations which carry density, but not spin density, and low-lying excitations that carry spin density, but not number density. And this is what's known as spin-charge separation. In general, these two low-lying excitations can have different speeds. And so they can separate spatially along the chain. So what I have here is just a sort of classical cartoon of what a density wave and a spin density wave would look like. So here on the left is the density wave, and you have just what looks like a sound wave propagating down the chain. And there are regions of excess density and regions of an absence of density. But there's no overall change in the spin density. Whereas for the spin wave, the opposite is true. You have local excesses in the spin density, but not in the number density. And as I said, in general, these two waves can propagate at different speeds, leading to spin-charge separation. These 1D systems are amenable to exact solutions at t equals 0 in the homogeneous case. So this Hamiltonian is known as the Yang-Godin Hamiltonian, and describes fermions in 1D interacting through contact interaction with two spin states. And the excitation spectrum splits into two types of excitation. As I said, so you have these charge excitations shown in green, that's this excitation spectrum, and it occurs at a characteristic velocity, which is the charge mode velocity. And you have a spin excitation spectrum, which occurs at a different velocity, the spin velocity. And you can calculate exactly what these the charge and spin velocities will be as a function of repulsive interactions. So this gamma here is related to the G1D, which is the strength of the 1D interactions, and is a dimensionless parameter which parameterizes repulsive interactions. So for zero interactions, the charge mode and the spin mode have the same velocity, whereas for repulsive interactions, the charge mode velocity increases and the spin mode velocity decreases. So there have been a number of experimental probes of Luttinger liquids and spin charge separation. Some of the first evidence was looking at power law conductance, which behaves as a power law of temperature and voltage, applied voltage. And this was done with carbon nanowires. And I believe that the carbon nanowires were actually grown here at Rice for this experiment. Further, there were indications of spin charge separation in etched wires and semiconducting heterostructures. But I think, in my opinion, the clearest demonstrations of spin charge separation in solid state were done in angle resolved photoemission spectroscopy experiments. In these experiments, what they do is that they use a photon to kick out one of the electrons in their chain, and then this results in a holon and a spin-on being produced. And they're able to see a two-peak structure in the excitation spectrum, which is indicative of the two different excitation modes. However, in solid state, they weren't able to tune the interactions particularly much, because all they can do is change the density of the electrons. And also, the amount of quantitative match between the beta ansatz calculations and their measurement is limited because of the electronic structure, complexity, and experimental defects, etc. So there's, I think, room for cold atoms to make a difference here and make some interesting observations. There have recently been a number of studies in 1D Hubbard chains in cold atoms. So a similar experiment done here using cold atoms now, where they remove one of the atoms from a 1D Hubbard chain and they watch how the hole propagates and how the spin excess propagates. So this is a very nice experiment where they showed the two different speeds of these two excitations. However, this excitation is well beyond the Luttinger liquid regime because it excites all energy modes, not just the low-lying excitations. So it's not it's not probing Luttinger liquid physics. Although the fact that they still see the spin charge deconfinement even at higher energy scales is quite interesting and shows that the spin charge separation is something that survives even at high energy scales. So now I'm going to switch tack and start talking about the experiments. I guess if there are any questions about my description of the Tomonaga-Luttinger liquid or the atomic physics, I can take them now. Yeah, so that's a good question. They just see this, two-peak structure.
Maybe repeat for the people online.
Okay. So the question was, how do the ARPAS experimenters know that one of these peaks is spin and one of them is charge? I don't think there's anything in this spectrum that will immediately let you determine one is spin versus one is charge. However, this calculation comes from beta ansatz calculation for the Hubbard or 1D Hubbard chain, and one of the peaks coincides with the energy at which they'd expect the spin mode, and one of them coincides with the energy they'd expect the charge mode. So that's the basis of that identification. But this excitation in general creates both excitations, so they can't create just one or the other. Any other questions? Okay. In which case, I will move on to discussing our experiments. So, as I described, we create this 2D optical lattice, which creates quasi-1D tubes. And we load a spin-balanced gas of lithium-6 fermions into these tubes. So there are two spin states. They're actually two hyperfine sublevels of lithium, but we can treat them as a spin 1/2 system. And these traps are highly elongated harmonic traps formed by the 2D lattice. There are interactions between the atoms that we can tune using a magnetic Feshbach resonance. So a Feshbach resonance is a resonance between two free atoms and a bound state, which allows you to tune the scattering between those two atoms to either be attractive or repulsive or even zero. So we are able to simulate the Hamiltonian, the Yang-Godin Hamiltonian. So apart from some residual axial harmonic confinement, which we have to deal with theoretically. And if our temperature is low enough and our chemical potential is low enough compared to the radial energy scales, then we can think of this as a quasi-1D system. And in our systems, we have about 40 atoms per tube.
So are there any structures within these two atoms, or is it completely random?
So there's a number profile that varies from tube to tube. So the number in the central tube will be, in general, be highest, and then it decreases as we go out radially.
Are there any structure within the tubes, or just random?
The tubes are in a square lattice configuration, and there's some tunneling between them, but we operate in some regime where the tunneling is quite small. So,
Why do you choose square?
the square lattice was basically just inherited from previous Hubbard model experiments in this apparatus. It doesn't matter because we're only really talking about one tube or individual tubes. So the technique we use is Bragg spectroscopy. This is a two-photon coherent process that delivers some amount of energy and momentum to the atoms. So basically what happens is that you have an atom and it undergoes a virtual excitation, which leaves it with some energy that's equal to the difference between the frequencies of the two photons. So we can provide some energy to the atoms, and we can also provide some momentum to the atoms. And the momentum that's delivered to the atoms is determined by the angle between the two Bragg beams. And in our experiment, we fix that to be some small value of Q compared to the Fermi momentum. The Bragg process leaves the internal state unchanged, so there's no spin flips. We're just kicking the atoms. And since we're applying a known amount of energy and momentum to the sample, this allows us to directly probe the dispersion relation. So what we do is we apply the Bragg kick along the tube axis. So here the tube axes are horizontal and the Bragg kick is to the left. This is an image of the cloud of atoms. It's a group of quasi-1D tubes without a kick after some time of flight expansion. So we release the atoms from the trap and they expand according to their momentum distribution, and we can image them using a CCD and a resonant light pulse. After applying the Bragg kick, some cohort of the atoms are kicked in the direction of the momentum transfer. And we can, by subtracting these two images, we can spatially resolve the kicked fraction. So what you have here in red is the excess of atoms that have been kicked, and in blue is the where those atoms were kicked from in the momentum distribution. So we can sum up the number of atoms that were kicked, and it turns out that that's proportional to the dynamic structure factor. So the dynamic structure factor basically tells you how the gas responds at a given momentum and at a given energy.
So I would expect, so I mean, the plots that are drawn over there are essentially showing the collective excitations in charge and spin, right?
Mm-hmm.
So this would come from the density-density correlation function and the spin-spin correlation.
Mm-hmm. Yes.
But which one is this?
Yeah, I will get to that. Trust me when I will explain, but it turns out that we can use a Bragg configuration that will only couple to the density-density dynamic structure factor, and we can use a Bragg configuration that couples only to the spin-spin dynamic structure factor. And so, for example, if we want to couple to the charge mode, which is the density-density structure factor, we would pick some momentum, which is given by the geometry of the beams, and then we would see some response of the gas given by the excitation spectrum. So this is what you asked. So we want to independently access the density dynamic structure factor and the spin density dynamic structure factor. And so this is what the density structure factor is and the spin density structure factor. This is just the general definition. So it's you can think of it as a Fourier transform of the density-density correlation or the spin-spin correlation. And it turns out that you can choose which one of these two you're accessing by a choice of detuning. So what's shown here by delta is the detuning of your Bragg beams from the resonance of that spin state with a excited state. So if you want to only couple to the charge mode, you want to use a large detuning for your Bragg beams from both of the two spin states. So your Bragg process is not sensitive to the spin because it's such a large detuning from both of the spin states. So you couple symmetrically to both spin states, and you're only sensitive to the density part of the dynamic structure factor. To measure the spin mode, you have to detune your beams midway between the two spin states. So now you have equal but opposite, you're applying equal but opposite forces on the two spin states, and you have an asymmetric coupling to the gas, and therefore you only couple to the spin structure factor. So this is the critical technique that allows us to measure both the spin mode and the charge mode. Yeah.
Yeah, so I mean, one key physics, I mean, people basically assume the change is infinity, right? So I mean, can you actually test the limit? I mean, how many atoms when you add it in, this limit is actually.
Yeah, I mean, that's a good question. So, in our samples, the maximum, so the question was, generally when you think about a 1D system, you're thinking about an infinite system. But the question is, can we go to smaller system sizes, finite system sizes, and do these Luttinger liquid properties, are they preserved, and how small can we go before we lose them? In our system, the peak occupation of a single tube is about 50 atoms, and that goes down to about 5 atoms on the edges. And so the median tube occupancy is about 30 atoms. And we still see Luttinger liquid physics with 30 atoms only. I think it could be interesting to go even lower and lower occupation to see at which point we no longer see spin charge separation, but that's not something we've done yet because we were trying to maximize our signal. But I can tell you, at least with 30 atoms, you definitely have Luttinger liquid physics. So previous work using Bragg spectroscopy to measure the charge mode dynamic structure factor. So this was actually done by Guido during his PhD, studying using ytterbium in 1D. So here they had a fixed repulsive interaction, and when they did the Bragg spectroscopy, looking at the charge mode, they saw a shift in the peak of their measured spectrum when they had two different spin states versus when they only had one spin state. And when you have one spin state, you don't have any interactions because of there's no S-wave interactions for identical fermions. Also, there's some work done in our group where they measured the charge mode structure factor using Bragg spectroscopy for variable interactions. And so here they were able to measure the charge mode velocities as a function of interactions in this region of this diagram. However, unfortunately, they were not able to excite the spin mode. And that's because the detuning that you need to use for the spin mode is set by your spin state splitting. And so it has to be exactly half of that. And the spin state splitting is not particularly large compared to the line width of the transition that's used for the Bragg process. So this led to a lot of absorption of Bragg photons, which basically destroys the sample. So they were not able to measure the spin mode. So in order to measure the spin mode, we had to implement some improvements. We did a couple of improvements. The first was to, instead of using the standard 671 nanometer red transition to the lowest lying excited state, which has a natural line width of 6 megahertz, we used a ultraviolet transition to the next excited manifold, the 3p manifold. And this transition has a natural line width, or an effective line width, that's about 8 times narrower. So this leads to an 8 times reduction in the scattering rate of photons. We also increase the state splitting by a factor of 2, simply by choosing a different pair of hyperfine states. And it turns out that there's a usable Feshbach resonance also with this pair of hyperfine states. So with both of these improvements, we got a total of a factor of 16 reduction in the absorption of the Bragg photons. And this was sufficient for us to be able to excite for the first time the spin mode. And so this is a schematic of what this kind of experiment looks like. So in red, I'm showing you the charge mode Bragg configuration, where we are detuned far from either spin state, and therefore we couple symmetrically to the gas. And this creates a density excitation, which then propagates down the tube. Instead, when we use the spin mode Bragg configuration, in which we have an antisymmetric coupling to the gas, we now have a spin wave that propagates down the tube, where you have some local excess of spin ups and a local excess of spin downs that propagates down the tube. So now, having described the experiment, I'll get on to our results. So the first result is on our work on spin charge separation. And so we measured the density and the spin density dynamic structure factors using Bragg spectroscopy. And that's what's shown here. So remember, we pick a fixed Q, and then we vary omega, the energy difference between the two photons. And this delivers different amounts of energy to the gas at a fixed momentum. And we observe how responsive the gas is at that energy. So the first thing to look at is at 0 interactions here. So this is an ideal 1D gas. And it turns out that the charge mode and the spin mode coincide. Their dynamic structure factors coincide for the ideal gas. So you can see that the peaks for these two are the same, but also if I lay these two on top of each other, the dynamic structure factors for both of these look the same.
So what determines the width of that peak?
There's a number of factors. The temperature, the finite momentum that we're using, the density inhomogeneity in our sample, and the finite pulse duration of the Bragg beam leads to some temporal broadening. But I will get to all of those. So yeah, these peaks shift in opposite directions as we increase repulsive interaction. So what I plotted here is this is the S-wave scattering length. You can think of it as just telling you how repulsive the gas is. So 0 is non-interacting, 500 Bohr is strongly repulsive. And the peak of this, the charge mode dynamic structure factor shifts to higher frequencies. And the peak of the spin mode dynamic structure factor shifts to lower frequencies. And that's as you expect, because for a repulsive gas, the charge mode velocity increases, and for a repulsive gas, the spin mode velocity decreases. These lines here plotted are calculations, and where the only free parameter is a global temperature of 250 nanokelvin for all of our samples, as well as scaling of each individual dynamic structure factor to the signal size. These calculations use Beidou-Ansat's results for the velocities, and they were done by Han Pu, Shiwen Guan, and a couple of Shiwen's former students. And as I described, the broadening, we had to account for various sources of broadening in these calculations. The first is the finite momentum, which leads to nonlinear effects in the Tomonaga-Luttinger liquid, which I will describe, as well as the finite temperature, as well as density inhomogeneity. So there's both inhomogeneity between tubes. We have different numbers of atoms in each tube. And we also have a harmonic axial potential, which leads to an inhomogeneous density along the tube. We also have a finite Bragg pulse. In our case, it was 200 microseconds, and that leads to temporal broadening of this dynamic structure factor as well. So the agreement here is really quite excellent and is beyond anything that's ever been measured for a Luttinger liquid in any experiment that I know. So a discussion of the nonlinear Tomonaga-Luttinger liquid. So back to this excitation spectrum from the beta ansatz calculations, you can see that the dispersion is not actually linear. There is some finite width to these excitations, and that's due to band curvature. And for the charge mode, that band curvature is proportional to q squared, and we had to take into account that charge mode band curvature in our calculation, and this was something that that Randy initially worked on with Thierry Giamarchi. The spin mode band curvature is proportional to q cubed, which is a smaller effect, and we neglected in these calculations. So showing the effect of the band curvature on the charge mode, what's shown here with the dashed line is a theory where we're assuming a strictly linear dynamic structure factor. So this is truly a delta function dynamic structure factor for the charge. And the solid line is the theory including the band curvature width. And you can see that the assuming a linear Luttinger liquid underestimates the width of the dynamic structure factor. Now for the spin mode, the nonlinear effects were even more serious. So there's this process called backscattering in which two spins can collide and exchange twice the Fermi momentum. So this is what it looks like in real space. You have two spins coming towards each other, and then they collide, and then they move away from each other. And it turns out that this process is impossible to linearize. So when you do the Luttinger liquid calculation, you end up with a Hamiltonian with a linear dispersion in the charge density, a Hamiltonian with a linear dispersion in the spin density, and then this extra term, which cannot be linearized. However, this term is marginally irrelevant in terms of the renormalization group, so typically this is neglected. However, we cannot neglect it at finite t, we found. And we found that we had to take into account this backscattering effect, and it leads to an interaction-dependent broadening of the spin mode only. And so here I'm showing you the theory including backscattering, and in the dashed line is the theory that does not include the backscattering. And you can see that it does not capture the high frequency tails of the spectrum that we measure. So this is really quite exciting because now we're beginning to go beyond the Luttinger liquid model, and we're beginning to see nonlinear effects. This was also evidence, also seen in simply looking at the outcoupled atoms from the gas. So what I'm showing here is an image of the atoms that are kicked out of the sample, both for the charge mode measurement and for the spin mode measurement, for zero interactions and for repulsive interactions. So you can see for zero interactions, both of them look quite similar. And for the charge mode, the width does not change much when we go to strong repulsive interactions. However, for the spin mode, there's some increase in that width. And we were able to model the increase in the width by using that interaction-dependent broadening of the spin mode dynamic structure factor due to backscattering. So this is nice because it all sort of hangs together. And what we see in the dynamic structure factors is also evident just by visually looking at the atoms. So here's a summary of all the data. What's shown here in red are the peaks of the charge mode dynamic structure factors, and in blue, the peaks of the spin mode dynamic structure factors. And so, as I said, for zero interactions, the peaks of those dynamic structure factors coincide, and as you increase repulsive interactions, the charge mode peak increases and the spin mode peak decreases. And what's shown here with the dashed lines are the peaks of those theory calculations. And there's really quite good agreement throughout this range. You'll see that at weak interactions, both speeds go down initially. This is really just because it's quite difficult to maintain a constant density and number profile at weak interactions in our system. So I think what's happening here is just that the number of atoms per tube in this sample is not quite the same as over here, which is leading to that drop. Yeah. Here. Yeah. So I think here it overestimates the spin mode velocity because we neglected the band curvature. So as I said, the spin mode has a cubic band curvature, and we neglected that. So I think if we included those results, this line would come down. Yep.
So you probably said it earlier and I missed it. Physically, how long is each tube?
So the Fermi radius is about 10 microns, so it's quite small.
That's how long the tube? That's how this diameter of the tube?
That's how long the tube is.
So, do you have any, I assume what happens in a finite tube is that these modes, when you excite them, they go and they hit the ends and bounce.
Yes.
Does that end up affecting anything, or are you measuring everything on timescales that are short enough that that's enough?
So the question is, first of all, how long is our tubes? They're 10 microns long. And then the follow-up question was whether we see these excitations bounce back off the harmonic confinement. And the answer is, if we wait long enough, we do. We just use a short enough pulse compared to the harmonic trapping period such that we don't see that. So that tells us how fast we need to apply this pulse. But certainly if we wait and hold, we see the atoms get kicked out one direction, and then they get kicked out the other direction, and then they come back.
And is that the actual speed of the
Yeah, so the question is, what is this? Yeah, so this is the speed of the charge mode and the spin mode, and it's related to the frequency, the energy, simply by Q, which is the momentum at which we're probing. So you can see in the most repulsive case, there's almost a factor of 2 difference between the charge mode velocity and the spin mode velocity.
I suppose what mine mentioned is how slow that is.
Yeah.
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 I'm used to electronic system, but this is
Yeah, so I mean, everything in cold atoms generally is far more dilute than in electronic systems, and the interactions far more weak. So our Fermi momentum is very small. It's given by the local density, and our local density is not very high.
So, did you try to go even further in the interaction?
Yeah, that's a good question. So we could not go much higher in interaction because eventually the atoms start undergoing 3-body collisions and forming molecules. So we're basically limited to this. And if we go back to that chart, we're probing this sort of region. So we're not able to, get such a massive difference and probe the really strong interaction region. Okay.
So how do you know the deviation that you see, is sort of backcutting instead of due to the finite size effect that you have? You don't have 50 atoms, right? You haven't done the test, you said, right?
Yeah, so the question is, how do we know that this broadening is due to a finite size effect rather than...
Yeah, due to max, you said due to max.
Yeah. Why is...
Yeah.
Right. Well, first of all, I would say that the charge mode, we don't see that at all. So I would expect, if it were a finite size effect to affect both the charge and the spin mode. I don't see why there would be a reason to only affect the spin mode. Whereas the backscattering is something that really only affects the spin mode. This process is not there in the charge sector. And we find, good agreement with what we'd expect based on that. And we see an interaction-dependent broadening. So it's really interaction-dependent.
So is it possible to actually use the fact that the spin mode has this unclock process to, if you wait long enough, like Doug was suggesting, and actually see the thermalization of the spin mode?
Yeah, so that's something we've tried to look at. The idea was maybe we can see the spin mode really, decaying out. We haven't really been able to. We find that even the charge mode sort of begins to diffuse after passing through the gas a few times, and I can't say exactly if that's due to Luttinger liquid physics, because we are kicking this packet, if we wait long enough, we're kicking this packet outside of, the center. and now you're beginning to see other things. So, not quite sure about it.
But isn't that a little subtle? I mean, so the backscattering is probably not actually going to thermalize you, right? Because the Hubbard model is
Right, yeah. This is, I mean, we're in 1D, yeah. Yeah.
There'd have to be some combination of backscattering plus harmonic.
Yeah. Okay. See how much time I have left. Okay, I'll quickly go through some of our results here. So the next question we had is what happens if we heat up the Lunger liquid? And because we have two different velocity scales, that translates into two different energy scales. And so you can define a spin energy scale that's lower than a charge energy scale. Up till now, all of our measurements have been where the temperature is below both of these scales, and that's what allows us to observe spin-charge separation. However, if you put the temperature between these two energy scales, you expect something called a spin-incoherent Lunger liquid. And in this liquid, in this regime, you end up having, a thermal average over different spin configurations where you begin to lose the spin correlations. If you go, of course, to temperatures above both scales, then you are in this thermal regime where you have both hole excitations and spin excitation. And so in this spin incoherent regime, you expect a propagating charge mode, but you expect that the spin mode does not propagate. And so we did some measurements of this system, and what we found was that in the spin incoherent regime, we lost spin charge separation. So the peaks and, in fact, the entire spectrum for both our symmetric and our antisymmetric excitations matched above a certain temperature, which is in this spin incoherent regime. This is a little bit surprising to us because we expected that the spin or the antisymmetric excitation should not couple to the system at all. Like I just told you, the spin mode should not propagate. So we expected that the antisymmetric excitation should not couple to the gas, but it still did. And it did so in a way that was pretty much identical to the symmetric excitation. So that was surprising to us. What we think may be happening is that when you have these spin fluctuations, you're averaging over samples which have local spin imbalance. And our Bragg selectivity depends upon having spin balance, because otherwise you are not you're not applying a symmetric or antisymmetric excitation. So it could be that our spin mode Bragg configuration is coupling to the charge mode in this regime. And that's why both Bragg configurations give us the same peak. Nevertheless, what we see is that there's certainly something different going on here, and at this temperature scale, we certainly don't have spin charge separation. And lastly, I'd just like to quickly talk about attractive interactions. So you can also do the beta-Ansatz calculation for attractive interactions. And here you have unlike spins, so opposite spins pairing up to form bound states. And the result of that is that the charge mode velocity halves at strongly attractive interactions. And it turns out that the spin mode becomes gapped because in order to propagate the spin mode, you would have to break up this bound state. So we've taken some preliminary measurements of the Bragg spectra in the attractive regime. And we see, excitingly, that the charge velocity is less than the spin mode velocity. And that's the first time I think anyone has ever measured that in a system. So we're probing this weak attractive regime here. A little bit surprising behavior where the charge mode velocity is increasing rather than decreasing. But we think that this is explained by the effect of attractions on the density. Because we have a harmonic confinement along the tubes, as we go to attractive interactions, the atoms like to clump up together. So the density goes up, so the Fermi velocity goes up. So this line, what I'm showing here is just a very simple calculation where we're looking at the center of a single tube with 25 atoms, and we're mapping what the charge mode velocity should be and the spin mode velocity should be. So this is a work in progress, but it's something that's pretty exciting for us. So the number of future directions for this experiment. So the first thing that we might want to change is the spin polarization. So far we've been working with spin balanced gases, but you can work with partially polarized gases as well. On the attractive side, this gives the full deferral Larkin of Chinnikov exotic superfluid state. where you expect to have a paired gas and and an unpaired gas with two different velocities. So you could call that charge separation. And on the repulsive side, you have a quantum critical point governed by the spin polarization. So there's the opportunity to observe critical phenomena here. Tunneling between the tubes, we could turn it on and would be interesting to see the effects of tunneling there. And also in 1D, as mentioned, the dynamics are integrable, and so you can use generalized hydrodynamics to explain excitations. And this has been done with bosons, but no one has done an experiment using spinful fermions. And that system is expected to be rich because of the presence of both spin and charge excitation. So to summarize, here's all our data showing spin-charge separation on the repulsive side and an inversion of that velocity hierarchy on the attractive side. We showed the role of interactions by working at zero interactions where there is no spin-charge separation, turning on interactions and seeing the spin-charge separation. We were able to make quantitative comparisons with calculations at a level that's never been done before in Luttinger liquids, and we saw signatures of the nonlinear Luttinger liquid. We've done some probes of the spin-incoherent Luttinger liquid regime where we see a suppression of spin-charge separation, and we've begun to examine the attractive side, and we've seen this inversion of the spin velocities. So with that, I'd like to conclude and thank everyone I work with, specifically Randy, whose lab I've worked in for the past 4.5 years, and we've had a lot of great success and also worked through a lot of failures. All these graduate students with whom I've worked, Daniel Cavazos and Yating Chang, have graduated and moved on. Ashish is still here, and we still work side by side in the lab. And of course, on the theory side, Han Pu and Xiwen Guan and their student, and Xiwen's former students, who did the calculations for the spin charge separation experiment. With that, I'd like to conclude and thank you and ask for any further questions.
Thank you, Ruwan. We have time for questions. Yeah, Matt?
So is there any way to measure the Luttinger parameter directly and or to directly see the fractionalization of the charge mode? Usually we need some type of one particle probe.
So the first question is there any way we can directly measure the Luttinger parameter? So basically, in order to calculate these dynamic structure factors, we have to do a beta ansatz calculation in which you have Luttinger parameters. The second question is, can we see any evidence of fractionalization? I think we would need to do something different where perhaps we excite the charge mode and then, perform some kind of quench, I don't know, to see that.
Yeah, I mean, the traditional thing would be to do some type of purely one particle equilibrium probe like RF, or I don't know if there's something better than RF spectroscopy, something where you're pulling out individual atoms. Is there a way?
We currently can't do that in this experiment. In a sort of Hubbard chain experiment, you certainly can. So that's what they saw. So, if you have a 1D Hubbard chain, you can pull out one atom and then you can see that excitation split into the charge excitation and the spin.
Right. But I mean, that's, so it's a question of whether you're looking at the spectral function is that's very sensitive to details. The tunneling density of states, which is a little bit closer to RF spectroscopy, is supposed to be a more robust prediction. So it's like locally measuring the energy dependence of one particle. But anyway, I see.
There are experiments where people have done local RF probes, for example, in homogeneous Fermi gases, in 2D. So it may be possible here, you're beginning to get to the stage where your signal will be very small because you're talking about a chain of a few atoms. Quite tough.
Other questions? One thing maybe that you could comment on is the lack of a pairing gap in the attractive side.
Yeah, so for all gamma less than 0, you expect there to be pairs. At gamma equals 0, the binding energy goes to 0. And so, for infinitesimally small gamma, the binding energy is infinitesimally small. And the binding length, the length of the bound state is infinitely long at this point in time. And so because of that size of the bound state, you end up having this smooth connection between this deeply bound state, where you have a deeply bound pair with half the velocity. But you have a smooth connection between those two. And so there are bound states here. And the question is whether we can measure the binding energy using RF. That's something that we've tried to do. And we do see a peak at roughly the right frequency. It's just that that binding energy is so small that it's quite comparable to the mean field shifts that we'd expect in our sample.
Yeah, Pengcheng.
Yes, so I have
Here, let me
naive
give you that.
question from a solid state physics point of view. So, I mean, people have seen this, and this one-dimensional physics has been well understood. It can be do exact calculation. People have seen, spin-on continuum. I mean, can you guys also see that? I mean, from really expand the dispersion. So far, you're basically looking at the, the low Q limit of the dispersion, right? I mean, what can you do to get the whole map?
So I think the question is about the higher momentum spin excitations.
Yeah.
So in principle, you would be able to do those with Bragg spectroscopy in the same way that we have done. Right now, we are limited to small Q just because of the optical access in our machine. We can't get to such large angles in our current setup to get to high momentum. But in principle, it should be possible. So you should be able to.
Oh, you mean that because of the technical?
Yeah, it's just a technical challenge. So get back to the excitation. So this is. Sorry.
Yeah, the blue part.
Yeah. So the question is about looking at excitations here or here, for example, measuring this whole thing out. Yeah, that's been done in solid state. Yeah. So I think if we are able to get Bragg beams into our chamber with the appropriate angle for that momentum, we would be able to do a Bragg measurement there.
So the calculation of the band of the backscattering process and other nonlinear processes, I don't know if I would consider those exact.
Right, they're not.
Those are not really exact calculations.
They're not.
Yeah, so I mean, I actually was very curious because the question that you might want to address, hopefully, is that by how many atoms will you increase the chance that the spin charge substitution will be positive? Because these are something that in the solid state people cannot do.
The five important thing, Jake, you see a frequency shift of two particles. So what do you want to look at?
I don't know. I'm just asking a simple question. Right? I mean, if you have two particles, if one particle is single particle, two particles are diamond. If you keep increasing it, it'd be interesting to, from a hypothetical point of view, right? It'd be interesting to know, at what point this 1D physics becomes really important.
I think in our systems, we have a bundle of tubes with some number profile. So we can't really precisely determine how many atoms are in each tube. We can do it on average for low numbers.
Any other questions? All right, if not, let's thank Ruwan again.